If you walked across the campus of the Delft University of Technology in the quiet hours of a cool Dutch night in 2015, you would have found nothing out of the ordinary. Just dark brick pathways, quiet trees rustling in the autumn air, and the silent outlines of university buildings. Yet beneath that calm surface stretched across a distance of 1.3 kilometers, a long and silent drama was playing out. In a basement on the southern edge of the campus, deep inside a stainless steel vacuum chamber, cooled down to near absolute zero, colder than the empty void between stars, sat a tiny synthetic diamond. Embedded inside its carbon crystal lattice was a single trapped electron. Its spin, a microscopic magnetic orientation, waited in the dark. 1.3 kilometers away, past lecture halls, parking lots, and sleepy avenues, inside another laboratory on the northern edge of the campus, sat a second diamond. It contained a second electron, held in the exact same cold, isolated stillness. The distance between them was not chosen at random. 1.3 kilometers meant that light itself, traveling at 300,000 kilometers per second, needed about 4.3 microseconds to cross the campus. That narrow window of time was essential. Every measurement, including the random setting of detector orientations, had to be completed before any signal could travel from one laboratory to the other and influence the outcome. Connecting these two isolated rooms was a thread of fiber optic cable, buried deep beneath the ground. There were no human voices in either laboratory. There were no eyes watching the particles through lenses. There was only the low, rhythmic thrum of cryogenic cooling systems, the subtle ticking of automated laser shutters, and the absolute silence of equipment operating in total isolation. Every few microseconds, a pulse of laser light hit the diamonds, prompting each electron to emit a single photon into the fiber optic line. At a central station between the two locations, a detector waited for those two faint particles of light to arrive at the exact same instant. The equipment was waiting for something extraordinary. It was attempting to link the two distant electrons into a single shared quantum state, and then measure them before any signal, traveling at the speed of light, could possibly pass between them across the campus. That experiment in 2015 did not discover a new force of nature. It did not create a new technology. What it did was much quieter and much more profound. It closed a crucial chapter in a case that had remained open for 80 years. A debate that began in 1935, carried on by some of the greatest minds in history, had finally been put to a physical test that left no room for escape. The data gathered that night delivered a verdict on one very specific, very comfortable picture of how the physical world operates. That experiment permanently eliminated one specific picture of reality. It has also never confirmed which of the remaining pictures is true, and those two statements are not the same thing. When the trial at Delft concluded, the evidence was clear. But what that evidence actually meant for the world we inhabit remained as deep a mystery as it was 8 decades ago. We are the unknown. Tonight, we step into an 80-year-old investigation where the experimental facts are indisputable, but the underlying nature of reality remains contested by every major school of thought. In this episode, we will carefully separate what has been proven by hard evidence, what has been ruled out forever, and what remains completely open to debate. Before we move deeper into the quiet halls of this mystery, if you enjoy these gentle midnight journeys into the strange architecture of the universe, please take a moment to follow the podcast on whichever app you are listening to right now. It is the single simplest way to support our work and ensure you never miss our future explorations. Because as this story unfolds tonight, the mathematics of the microscopic realm never stumbles. The equations agree, the stories do not. To understand why the most accurate theory in the history of science has divided its own creators into rival camps, we must first look at the machine itself. We must examine a framework so extraordinarily precise that it powers every computer, every laser, and every digital signal on Earth, yet so quiet about its own meaning that it leaves us standing in the dark. You do not need to travel to a laboratory in Delft to encounter quantum mechanics. You are surrounded by it at this very moment, in the quiet room where you are listening right now. Look around in your mind at the familiar objects that fill your space. The pale glow of a smartphone screen resting on a table, a small indicator light on a speaker, a clock ticking quietly in the hall. None of these everyday items would function for a single second if the microscopic world behaved according to traditional physics. Consider the telephone near your hand. Inside its casing sits a silicon chip containing billions of microscopic transistors. These transistors do not control electricity by pushing physical gates back and forth. They rely on the wave-like behavior of electrons moving through a crystal lattice of silicon. Engineers design the chip around forbidden energy gaps and exploit quantum tunneling, a phenomenon where subatomic particles slide through physical barriers that classical physics says they should never cross. Every digital image stored in your memory, every message sent across the air, relies on millions of electrons performing this invisible dance billions of times every second. Or consider the faint, steady beam of light inside a laser pointer or optical player. In an ordinary lamp, excited atoms release light in a chaotic jumble of random directions and mismatched colors. But inside a laser, electrons jump between precise energy levels. When one electron drops down an energy step, it releases a photon that encourages neighboring electrons to drop at the exact same instant, emitting identical photons in perfect unison. The result is a focused thread of light that can read microscopic grooves on a disk, transmit data through undersea fibers, or guide a surgeon's instrument with delicate precision. Even the color of a modern LED bulb comes from these atomic steps. By tailoring the materials inside the diode, physicists select the exact distance an electron falls, dictating whether it releases a warm yellow glow or a cool blue light. Out in the sky, high above the clouds, atomic clocks circle the Earth inside satellite hulls. Inside each clock, cesium atoms are bathed in microwave radiation, tuned to a frequency where electrons jump between energy states over 9 billion times every second. That atomic pulse is so stable, it will not lose a single second in tens of millions of years. It is that microscopic rhythm that allows your phone to calculate your location on a dark road to within a few feet. And if you have ever rested inside a magnetic resonance imaging scanner, listening to its loud, rhythmic thrumming, you were experiencing quantum physics at the scale of your own body. The machine surrounds you with a magnetic field that aligns the quantum spins of hydrogen protons at the heart of water molecules in your flesh. A pulse of radio waves tips those protons off balance, and as they relax back into alignment, they whisper back tiny radio signals. A computer translates those atomic echoes into detailed maps of soft tissue without ever touching a scalpel. The reach of this theory extends upward into the cosmos and downward into the structure of matter. Consider a sample of granite deep inside the Earth, slowly emitting heat over millions of years through radioactive decay. Inside an unstable nucleus, an alpha particle is trapped behind a wall of nuclear force. Under classical laws, the particle could never escape. It lacks the energy to climb over the barrier. But because the alpha particle is also a wave, its presence is not confined to one side of the wall. Its wave function bleeds slightly through the barrier, giving it a tiny chance of appearing on the outside. Day after day, the wave presses against the wall until suddenly, without breaking the barrier, the particle appears on the outside and escapes. That gentle quantum leak is what warms the interior of our planet, driving continental drift and geothermal springs. Look further outward, to the sun shining in the daytime sky. The sun is powered by nuclear fusion, protons smashing together in its core to form helium, releasing vast floods of energy. Yet the temperature at the center of the sun is actually not hot enough to force two positively charged protons past their electrical repulsion under classical rules. They ought to bounce off each other like steel marbles. The sun shines only because quantum tunneling allows protons to occasionally slip past that electrical wall, fusing together and radiating the heat and light that makes life on Earth possible. Below all of this lies chemistry itself. The reason a table is solid, the reason water is liquid, the reason carbon atoms string together into chains to build DNA comes down to how electrons arrange themselves around atomic nuclei. Quantum mechanics dictates that electrons cannot all collapse into the lowest energy level. They must fill specific atomic shells in an orderly sequence. That restriction gives the periodic table its shape. It explains why sodium reacts violently with water, why gold does not tarnish, and how chemical bonds form when atoms share outer electrons. Chemistry is quantum physics expressed at the scale of molecules. The predictive power of this theory is staggering. When physicists use quantum electrodynamics to calculate the magnetic properties of an electron, the mathematical prediction agrees with experimental measurements to roughly 12 decimal places. To appreciate what 12 decimal places means, imagine measuring the distance from New York City to Los Angeles. Roughly 3,000 miles, and getting an answer so accurate that your error is less than the width of a human hair. No other theory in human history has been subjected to such relentless testing. Particle accelerators have smashed subatomic fragments together at nearly the speed of light. Superconducting circuits have been cooled to within thousandths of a degree of absolute zero. Optical lattices have trapped single atoms in grids of laser light. Across all those decades, quantum mechanics has never failed a single experimental test. Not once. There is no serious physicist on Earth who argues that the mathematical machinery of quantum theory is broken. The math works. The calculations produce correct numbers every single time. Yet despite this practical consensus, a quiet crisis has simmered at the heart of physics for nearly 100 years. Because as soon as you step away from the workbench and ask what those equations mean, agreement instantly vanishes. To understand why, we must make a sharp distinction between two things that are often blurred together: the mathematical formalism of quantum mechanics and the interpretations of quantum mechanics. The formalism is the collection of mathematical rules that every physicist learns. It includes the wave equation that tracks how quantum states evolve smoothly over time, the mathematical space used to represent possible states, and the rule for turning wave amplitudes into ordinary probabilities. This formalism is a universal tool. A physicist in Tokyo, a researcher in London, and an engineer in California can sit down at their desks, input the same initial numbers, and arrive at the exact same numerical result. The disagreement begins when we ask what those equations are actually telling us about the world when we are not looking. The equations tell us how to calculate the probability of finding an electron in a specific spot, but they do not tell us whether the electron was actually in that spot before we looked, or whether it was spread out across space like a cloud, or whether it existed in multiple places at once. The math gives us a recipe for predicting what our instruments will read. It does not tell us what reality looks like between measurements. This is the divide between formalism and interpretation. Two physicists can agree completely on the math and arrive at identical predictions for an experiment. Yet one might believe the particle was guided by an invisible wave through a single path, while another believes the particle split and traveled through multiple parallel universes at the same time. They share a single set of equations. They hold entirely incompatible visions of reality. The competing interpretations are not different theories fighting over different numbers on a printout. They are different stories trying to make sense of the exact same numbers. And the questions these stories try to answer cut straight to the core of what we mean by reality. Does a microscopic particle possess a definite position, momentum, or magnetic orientation before an instrument interacts with it? Or do physical properties only come into existence at the moment of observation? Does the act of measurement cause a real, physical change in the universe, collapsing a cloud of possibilities into a single concrete outcome? Or is measurement simply an illusion, a moment where our own awareness becomes tied to one branch of an ever-splitting cosmos? And where does probability come from in a universe governed by smooth, deterministic equations? Is probability a fundamental feature of nature, or is it merely a reflection of our own partial ignorance? We have never found an experimental flaw in the mathematical machinery of quantum physics. We have also never agreed on what that machinery means for the world we inhabit, and those two facts continue to stand side by side. To understand why these questions have proved so stubborn and why they cause such deep philosophical discomfort, we cannot remain in the present day. We must look back to the world as it was understood before quantum mechanics arrived, a world where physics offered a comforting, solid picture of reality that felt as reliable as the ground beneath our feet. Before the strange rules of quantum physics were uncovered, the physical world seemed to operate according to a set of quiet, self-evident expectations. These principles were not written down in formal manifestos or debated in philosophical halls. They did not need to be. They were so deeply intuitive, so thoroughly confirmed by daily human experience, that scientists rarely felt the need to state them at all. They were simply assumed to be the foundation of reality itself. The first of these implicit rules was realism, the simple conviction that physical objects possess definite, objective properties, whether anyone is looking at them or not. Consider a heavy granite stone resting in the middle of an empty forest clearing. If you walk away from the clearing and leave it behind in total solitude, you assume without hesitation that the stone remains exactly where you left it. It retains its weight, its gray texture, its precise location among the fallen leaves, and its physical volume. It does not dissolve into a haze of possibilities simply because human eyes have left the woods. Similarly, when astronomers step away from their telescopes at dawn to sleep, they do not doubt that the planet Jupiter continues along its smooth elliptical path around the sun. The solar system does not wait for an audience to decide where its planets ought to be. Its physical state is independent of human attention. Hand in hand with realism came the principle of locality. This was the understanding that physical influences must travel continuously through space, moving from one point to the next at a finite speed. An event taking place in one location cannot instantly alter an object sitting somewhere else without a physical carrier. A wave, a particle, or a field, traveling across the distance between them. If a lamp lights up across a dark room, it is because light waves have traversed the space between the bulb and your eyes. Nature does not allow instantaneous jumps across empty distance. Alongside realism and locality was the assumption of causality, the steady, unyielding sequence in which cause always precedes effect. The past shapes the present, and the present determines the future. A vase shatters on a stone floor because it was dropped an instant earlier. It does not shatter in anticipation of being dropped tomorrow. Then came separability. If two physical objects are separated by a wide distance, each of them possesses its own complete, independent physical state. What happens to a pebble on a beach in Scotland is entirely distinct from what happens to a grain of sand on a coast in Japan. The two items might share a past history, but once separated, each exists in its own right, fully defined by its own local properties. And finally, overarching all of these was observer independence. The physical world was understood to exist out there, objectively, as a stage upon which natural forces played out. Human beings were mere spectators who could step onto the stage to observe, measure, and record, but whose presence was not required for the play to continue. The universe was not created by observation, nor was it altered by the simple act of looking. In the 17th century, Sir Isaac Newton gathered these natural expectations into a mathematical framework that reshaped human thought. Under Newtonian mechanics, the universe was pictured as a magnificent clockwork mechanism. Every star, every planet, every drop of water, and every grain of dust was governed by precise, universal laws of motion and gravity. If you pushed a wooden cart down a hill, its trajectory was dictated entirely by its mass, the slope of the ground, the friction of its wheels, and the resistance of the air. If you knew the force applied to an object, you could predict its exact movement with total certainty. This vision reached its grandest expression in the idea of total mechanical determinism. In theory, if an all-knowing intellect could know the exact position and momentum of every atom in the cosmos at one single instant, it could use Newton's equations to calculate the entire past and future of the universe with absolute perfection. Every eclipse that had ever darkened the Earth, every leaf that would fall in an autumn 3 centuries from now, was already locked into the current state of the world, like the teeth of a giant gear train. Yet it is important to draw a clear distinction between a universe being deterministic and a universe being predictable by human beings. The two ideas are not the same thing. Consider the weather outside your window tonight. The Earth's atmosphere is governed entirely by classical equations of fluid dynamics, temperature, and pressure. Air molecules move and collide according to strict physical laws. Yet predicting whether it will rain 3 weeks from today remains notoriously difficult. This difficulty does not arise because the atmosphere is inherently indecisive. It arises because the atmosphere is a chaotic system. A microscopic variation in the initial conditions, the gentle flutter of a bird's wing in one valley, can amplify over days and weeks into a storm on another continent. We struggle to predict the weather far in advance simply because we lack the computational power and the precise, detailed information needed to track every air molecule. The atmosphere always has a definite physical state. It is our knowledge of that state that is incomplete. And if you drift off somewhere in here, that is perfectly all right. This story will still be waiting when you return. This distinction reveals the true nature of probability in the classical world. Whenever classical physics used probabilities, it was always a statement about human ignorance, never a statement about reality itself. Imagine a playing card placed face down on a polished wooden table. You are asked to guess whether the card is red or black. Before you flip it over, you might say there is a 50% chance it is red and a 50% chance it is black. But that 50% probability does not mean the card is hovering in a strange, half-red, half-black state while resting on the wood. The card is already entirely red or entirely black. Its identity is fixed, solid, and absolute. The probability exists only inside your mind, reflecting your lack of information. The moment you flip the card over, your knowledge changes, but the physical card itself undergoes no transformation whatsoever. The same is true for a die rolling across a felt table. The die tumbles through the air according to gravity, air resistance, and the force of your hand. If a physicist had microscopic sensors capable of measuring the exact angle, velocity, and surface friction of the die the instant it left your fingers, the final number facing up could be calculated before the die ever touched the table. We call a die roll random only because human senses are too coarse to track the microscopic forces at play. Even the study of gases in 19th century physics followed this exact logic. When scientists described the air inside a warm room using terms like temperature and pressure, they were using statistical mechanics, averaging the behavior of trillions of colliding nitrogen and oxygen molecules. They used averages because tracking every single molecule was practically impossible. But no one doubted that every single molecule possessed a precise location and a precise speed at every moment. Statistical averages were a convenient shorthand for human observers, not a fundamental feature of nature. Even the discovery of waves in the 19th century fit comfortably inside this classical worldview. Physicists understood ripples spreading across a quiet pond as physical displacements of water molecules moving up and down. They understood sound traveling through a room as mechanical waves of compression and rarefaction passing through the air. And when James Clerk Maxwell demonstrated that light was an electromagnetic wave, it was understood in the exact same physical terms. An electromagnetic wave was a continuous, real disturbance in electric and magnetic fields, carrying energy and momentum smoothly through space. A classical wave was not a mathematical abstraction. It was a real physical phenomenon spread out across space, moving according to precise field equations. It was not a list of possibilities. It was a physical state. Consider a heavy iron cannonball fired across an open field on a foggy morning. As it leaves the cannon's mouth, it disappears into a dense, white mist. An observer standing near the target area cannot see the cannonball as it travels through the gloom. They hear the distant boom, wait in silence as seconds pass, and then hear the heavy thud as the iron sphere strikes the damp earth. During those seconds of silence in the fog, no human eye witnessed the flight of the cannonball. Yet classical physics assured us that the cannonball followed a single, continuous, parabolic arc through the mist. It was at one specific point in space at every microsecond of its flight. Its trajectory was real, solid, and continuous, completely independent of whether anyone could see through the fog to track it. These classical expectations, realism, locality, causality, separability, and observer independence, were not arbitrary philosophical choices. They were the very vocabulary of human reason. They framed how we thought about space, time, matter, and motion for hundreds of years. We have never found a flaw in the logic that built this classical worldview. We have also discovered that nature, at its deepest level, refuses to obey it. And those two statements are not in contradiction. The classical picture of reality was not abandoned because scientists grew tired of it, or because philosophers persuaded them to try something new. It broke because, as the 19th century gave way to the 20th, physical experiments began to produce results that simply could not be forced into the classical mold, no matter how hard physicists tried to bend them. The classical world did not shatter all at once. It fractured line by line through a series of subtle experimental clues gathered across the opening decades of the 20th century. In 1900, Max Planck discovered that energy is absorbed and emitted in discrete packets he called quanta. In 1905, Albert Einstein showed that light itself behaves during the photoelectric effect as individual packets of energy. In 1913, Niels Bohr revealed that electrons inside an atom jump between specific quantized energy levels. In 1924, Louis de Broglie proposed that solid matter, electrons, protons, entire atoms, must also possess a wave nature. In 1925, Werner Heisenberg constructed matrix mechanics, building physics out of mathematical tables of observable quantities. And in 1926, Erwin Schrödinger formulated a wave equation, describing how these quantum states evolve smoothly through time. Out of these discoveries emerged a single, extraordinarily powerful mathematical machine that every working physicist relies upon today. At the center of this machine sits the wave function. The wave function does not provide a list of predetermined properties. It does not state that an electron is resting at 5 millimeters along a ruler with a speed of 10 meters per second. Instead, it is a complex mathematical expression containing complete information about all possible outcomes of a future measurement, along with the mathematical relationships between those possibilities. To hold these possibilities, physicists construct a mathematical space called Hilbert space. It is important to be clear about what Hilbert space is not. It is not a physical region of space hidden behind distant stars, nor a secret realm tucked beneath the floorboards of our universe. Hilbert space is an abstract mathematical construction where every independent possibility open to a system adds another dimension. If a particle has two possible states, its Hilbert space has two dimensions. If it has 1,000 possible paths, its Hilbert space expands into 1,000 dimensions. Within this space, a quantum system can exist in what physicists call a superposition. Superposition is often described in casual conversation as a particle being in two places at once, but that phrasing misleads. In quantum mathematics, a superposition means a single state is constructed out of a combination of other states, weighted by numbers called probability amplitudes. These amplitudes are complex numbers, possessing both a magnitude and a phase. Because they have a phase, amplitudes interact with one another. When two amplitudes meet, their phases can align, reinforcing one another, like ocean waves meeting crest to crest. Or their phases can oppose, completely canceling each other out like a crest meeting a trough. This cancellation and reinforcement is what physicists call interference. To understand why a quantum superposition is fundamentally different from ordinary classical randomness, consider a simple thought experiment. Imagine a wooden box divided into two compartments, a left side and a right side. A small red ball is placed into the box. Half the time, the ball is placed on the left, half the time on the right. The box is sealed shut and handed to you. You do not know which compartment holds the ball. You might say there is a 50% chance it is on the left and a 50% chance on the right, but this is a purely classical statistical mixture. The ball is always in one specific compartment. You simply lack the information to know which. If you open the left compartment and find it empty, you learn that the ball was on the right all along. No physical change took place inside the box when you opened the lid. Now consider a quantum particle placed inside that same divided box in a true quantum superposition of left and right. This is not a case of the electron being on the left while you remain ignorant, nor is it on the right. The left state amplitude and the right state amplitude exist simultaneously, maintaining a precise mathematical phase relationship. If you take a classical box with a ball hidden on one side and open two holes to let the contents spill through, you simply get two dull mounds, one behind each opening. But if you allow the two components of a quantum superposition to spill out through two narrow slits, something extraordinary happens. The left amplitude and the right amplitude overlap across space. Where phases match, they reinforce. Where phases oppose, they cancel out completely. The pattern that forms on the screen is an interference pattern, alternating bands of bright signal and dark silence. No classical mixture of a ball hidden on the left or the right could ever produce those dark bands of complete cancellation. A classical mixture can only add probabilities together. It can never subtract them. The evolution of this wave function over time is governed by the Schrödinger equation. And here lies one of the great ironies of quantum physics. The Schrödinger equation itself is entirely smooth, continuous, and completely deterministic. It does not roll dice at every microsecond. If you provide the equation with the precise wave function of an isolated system right now, it calculates the exact wave function at any future moment with absolute certainty. The wave aspect of quantum mechanics is as deterministic as Newton's laws. The randomness enters only when we connect this smooth wave to an experimental outcome using a rule formulated by Max Born. The Born rule states that to find the probability of observing a specific result, you must take the corresponding complex amplitude and calculate the square of its magnitude. This step is crucial. Amplitudes themselves are not probabilities. Probabilities are always positive numbers between 0 and 1. Amplitudes, with their positive and negative phases, exist in a deeper mathematical layer. It is precisely because amplitudes are not probabilities that they interfere and cancel before the Born rule converts them into the positive probabilities of an actual measurement. When a physicist wants to extract physical quantities from this wave, such as position or momentum, they use mathematical operators, In classical physics, you can measure location and speed at the exact same instant. In quantum mechanics, the operator for position and the operator for momentum do not commute. The order in which these operations are applied changes the mathematical result. This non-commutative property leads directly to Werner Heisenberg's uncertainty principle. Stated simply, the more tightly localized a wave function is in space, the broader and more spread out its momentum components must become. Conversely, the more precisely its momentum is defined, the more widely its position spreads across space. The uncertainty principle is not a complaint about clumsy laboratory equipment. It is not an admission that our microscopes are too crude or our hands too unsteady. It is a fundamental property of wave mathematics. Just as a short, sudden sound pulse cannot have a single, pure musical pitch, a localized quantum wave cannot have a single, precise momentum. When two or more quantum particles interact, the mathematical machine reveals another feature: entanglement. In classical physics, two separated objects always possess their own individual physical states. But when two quantum particles interact, their individual wave functions merge into a single, unified wave function in a higher dimensional Hilbert space. The combined system can no longer be factored into independent descriptions for particle A and particle B. They become bound into a shared physical identity. A measurement performed on one part of an entangled pair instantly constrains the possibilities open to the other, regardless of distance. And when a physicist needs to describe a quantum system where some information has been lost to the surrounding environment, they use a tool called the density matrix, tracking both pure superpositions and ordinary statistical ignorance. Close your eyes for a moment and listen to how this mathematical machine reveals itself in a real laboratory. Imagine an experiment where a stream of particles is fired toward a barrier with two narrow, parallel slits. On the far side sits a detector screen sensitive to individual impacts. If you turn down the intensity until only one particle is released at a time, you might expect wave behavior to vanish. But it does not. Listen to the detector screen. You hear a single, sharp click. A particle has arrived at one precise point. Then silence. A second passes, and another single click sounds at another point. Click, click, click. Each impact is completely localized, arriving like a tiny, isolated bullet. The particles arrive one by one, separated by seconds of absolute quiet. There is no continuous wave washing over the screen. There are only individual, point-like events. Yet, as the hours pass, as thousands of these solitary clicks accumulate, something mesmerizing emerges on the record. The impact points do not pile up in two simple mounds behind the slits. They align into alternating stripes, dense bands where thousands of clicks have landed, separated by dark, quiet gaps where almost no particles have ever touched. Each particle arrived as an isolated, indivisible point. Yet the amplitudes that decided where each click could land had somehow passed through both slits. Whether the particle itself traveled through both openings or whether something else did is precisely the argument we have not yet had. This is the mathematical machine of quantum physics. It produces the correct statistics every single time. It guides the design of our microchips, explains the stability of our atoms, and predicts the outcomes of our experiments with staggering accuracy. Every school of thought in modern physics uses this exact same math, yet this machine contains a profound silence. It tells us how to calculate the probability of where a click will sound. It remains completely silent on whether the wave function is a physical object rippling through reality or merely a ledger of human expectations. The equations agree, the stories do not. To understand why this mathematical silence has driven physicists into fierce, enduring rivalries, we must examine the first great attempt to give the machine a voice and ask what happens to the wave function when someone finally looks. At the heart of the quantum mathematical machine lies a single, central question that has lingered for nearly a century. What is the wave function actually? The mathematical equations tell us how to calculate it, how to evolve it forward through time, and how to square its amplitudes to extract probabilities. But the math itself remains stubbornly quiet about what kind of entity the wave function is supposed to be. Is it a physical object existing out in the universe like an electric field or a gravitational wave? Or is it merely a mathematical tool residing entirely in our minds like a ledger of expectations? To navigate this question, physicists generally divide the possibilities into two main ways of thinking. The first approach is what philosophers and physicists call an ontic view. The word comes from the ancient Greek root for being or existence. Stated simply, an ontic view claims that the wave function corresponds directly to something physically real in the objective universe. If you change the wave function of an electron, you are not just updating your own personal knowledge, you are altering a real physical state of affairs out in the world. On this view, the wave is as real as a drop of water, a magnetic field, or a block of lead. The second approach is the epistemic view. This word comes from the Greek root for knowledge or understanding. An epistemic view claims that the wave function does not represent a physical object at all, but rather a state of knowledge, information, or belief. Consider a weather forecast readout on the evening news. The forecast might report a 70% chance of rain in your city tomorrow afternoon. That forecast is an epistemic statement. It summarizes the available satellite data, atmospheric pressure readings, and wind speeds, translating our current state of information into a prediction. If a new satellite image arrives an hour later, meteorologists might update the forecast, dropping the chance of rain down to 10%. When that number changes, no physical wave swept across the sky to erase the rain. The atmosphere itself did not undergo a sudden, magical transformation. What changed was our state of knowledge. On an epistemic view, the quantum wave function behaves in much the same way. It is a calculation tool that tracks what an observer knows, or can expect to measure, about a system. This distinction immediately raises the question of completeness. If the wave function is an ontic, real physical entity that provides a complete description of nature, then there is nothing deeper to find. The randomness we observe is a fundamental feature of the universe. But if the wave function is merely epistemic, an incomplete summary of our knowledge, then there must be something deeper underneath. There must be hidden variables, pre-existing physical properties, such as a particle's exact location or momentum, that exist continuously even when our wave function fails to list them. Yet, any attempt to treat the wave function as a real, physical wave runs into a formidable problem, one that becomes obvious as soon as you look at systems containing more than a single particle. Think of a sound wave or a ripple on a pond. A sound wave moves through three-dimensional space, up and down, left and right, forward and back. You can point to a spot in a room and say that the sound wave is compressing the air at that specific location. The wave function of a single quantum particle can also be mapped onto ordinary three-dimensional space. But as soon as you add a second particle, the math changes completely. The wave function of a two-particle system does not live in three-dimensional space. It lives in a six-dimensional mathematical space called configuration space. 3 spatial coordinates to locate the first particle and 3 coordinates to locate the second. If you add a third particle, the space expands to 9 dimensions. If you consider a modest system of just 100 interacting particles, no more than a single small molecule, its wave function exists in a space of 300 dimensions. This is the configuration space problem. If the wave function is a physically real object rippling through nature, it does not ripple through the three-dimensional space of our everyday experience. It exists in a vast, higher-dimensional landscape, and anyone who claims the wave function is physical must answer a perplexing question. How does a wave residing in a 300-dimensional mathematical space give rise to the familiar three-dimensional world of wooden tables, laboratory instruments, distant stars, and human observers? Faced with this challenge, some physicists prefer the ensemble interpretation. This view claims that the wave function does not describe a single, individual particle at all. Instead, it describes a vast, theoretical ensemble of identically prepared systems. Just as saying the average household has 2.4 children tells you nothing about any specific family, the wave function tells you only about the statistical distribution of a large collection of experiments. The ensemble view feels comfortably classical. It reassures us that individual particles might still possess definite properties, while the math simply handles the statistics. Yet this comforting picture faces severe pressure from quantum phenomena like single particle interference and entanglement, which make it exceedingly difficult to view the wave function as mere classical ignorance about pre-existing properties. Other physicists take an even more cautious path, known as instrumentalism or pragmatism. An instrumentalist declines to make any sweeping claims about what exists behind the scenes. To them, quantum mechanics is not a picture of reality. It is a reliable set of instructions for connecting experimental setups with detector readings. You input the initial conditions of your apparatus, run the calculation, and obtain the probability of a specific outcome. The strength of instrumentalism lies in its intellectual discipline. It refuses to invent unobservable entities or speculate about what happens in the dark, but its weakness is that it leaves many thinkers deeply unsatisfied. For many scientists, the ultimate goal of physics is not merely to construct a reliable instruction manual or a successful calculation tool, but to understand what the universe is actually made of when no one is looking. For decades, the debate between ontic and epistemic views remained largely a matter of personal preference. But in 2011, three theoretical physicists, Matthew Pusey, Jonathan Barrett, and Terry Rudolph, published a mathematical result that brought fresh clarity to the discussion. Their paper, which appeared in Nature Physics in 2012, became known as the PBR theorem. The PBR theorem targeted a specific popular class of epistemic models that claimed the wave function was merely incomplete knowledge about a deeper, underlying physical state. Pusey, Barrett, and Rudolph proved mathematically that if an epistemic model obeys certain natural assumptions, it cannot reproduce all the predictions of quantum mechanics. Specifically, they showed that if two quantum states are prepared differently, their underlying physical states cannot overlap in a way that allows the wave function to represent pure ignorance. In plain language, if quantum mechanics is correct, systems prepared in different quantum states must correspond to genuinely distinct physical realities. Yet, it is vital to understand what the PBR theorem does and what it does not do. The theorem does not prove that the wave function is a simple, physical wave in three-dimensional space. Like all mathematical theorems, its conclusion rests firmly on its initial assumptions. The most critical of these is known as preparation independence, the assumption that when two quantum systems are prepared independently in separate laboratories, their underlying physical states are also completely independent. If a model rejects or modifies preparation independence, or if it redefines the nature of the underlying physical state, it can step outside the reach of the PBR theorem. The theorem significantly constrains the space of plausible epistemic models, but it does not terminate the debate. It narrows the options without delivering a final verdict. Physicists share an extraordinary worldwide consensus on how to use the wave function to calculate experimental outcomes. They have also never reached a consensus on what the wave function actually represents, and those two statements continue to stand side by side. This disagreement is not a sign of failure. It is a reflection of how deeply quantum mechanics challenges our basic concepts of existence, and the question becomes most acute when we turn our attention away from isolated subatomic particles and apply the rules of quantum mechanics to the very measuring instruments we use to observe them. The debate over quantum interpretations does not arise from a lack of mathematical rigor. It arises because of what happens when we take the mathematical machine of quantum mechanics completely seriously and apply it not just to a single subatomic particle, but to the very equipment attempting to measure it. This is the measurement problem, and it is the hinge upon which every major school of quantum thought turns. To see how the problem takes root, consider a simple experiment built in a quiet laboratory. Imagine a single particle prepared in a true quantum superposition of two distinct locations, a left path and a right path. In its path, we set up a macroscopic detector. The detector is fitted with two indicator lights, a red light designed to flash if the particle passes on the left, and a blue light designed to flash if the particle passes on the right. Before the particle arrives, the detector rests in a neutral state. Its lights are dark. Now, let the particle enter the instrument. If we assume that both the microscopic particle and the macroscopic detector are composed of atoms governed by the standard, smooth equations of quantum mechanics, we must apply the Schrödinger equation to the combined system. When we do, the linear math gives a precise result. The particle does not trigger just the red light, nor does it trigger just the blue light. Instead, the particle and the detector become entangled. The combined system evolves into a superposition containing two distinct branches. One branch where the particle traveled on the left and the red light flashed, and a second branch where the particle traveled on the right and the blue light flashed. Nothing in that smooth, continuous mathematical evolution steps in to select one single branch over the other. The linear equation simply keeps both possibilities alive, expanding the superposition to encompass the detector. This is where John von Neumann exposed a troubling logical progression known as the measurement chain. If you argue that the detector is too small to be considered a proper measuring instrument, you can connect it to a larger computer. But according to the linear equations of quantum mechanics, the computer simply joins the entangled state. Its circuit boards, memory banks, and monitor screen enter a superposition of displaying the red result and the blue result. If a scientist walks into the laboratory and looks at the computer screen, the measurement chain does not stop there. Light waves bounce off the monitor, enter the scientist's eyes, trigger chemical reactions in the retina, and travel as electrical impulses along the optic nerve into the brain. Under the strict equations of quantum theory, the scientist's brain states and physical memory become entangled with the computer, the detector, and the original particle. The mathematical formalism provides no natural boundary, no physical threshold, and no logical cutoff where a cloud of entangled possibilities suddenly converts into a single, definite reality. The chain simply extends outward, threatening to engulf everything it touches. Yet this mathematical prediction stands in direct conflict with everyday human experience. This is the definite outcome problem. When a human scientist looks at an instrument, they never experience a blurred, contradictory superposition of two outcomes at once. They do not see a red light and a blue light flashing simultaneously in a single, confused awareness. The pointer always settles on one direction. The digital screen displays one specific number. The scientist writes a single line in their notebook. The fundamental question of the measurement problem is not, how are the other possibilities hidden from our sight? The question is, why does one single outcome become a concrete, experienced reality at all? Closely tied to this is the preferred basis problem. Mathematically, a quantum superposition can be rewritten in many different equivalent sets of reference states. Yet when we look at the macroscopic world around us, physical instruments always settle into very specific, familiar choices. A pointer pointing left or right, a light being on or off, a cat being alive or dead. The formalism itself does not explain why nature consistently selects these familiar, spatially localized outcomes rather than some bizarre, smeared combination of physical possibilities. In 1935, Erwin Schrödinger constructed a famous thought experiment to highlight this exact absurdity, an illustration that has since become one of the most widely misunderstood ideas in popular science. Schrödinger imagined a cat placed inside a sealed steel chamber, along with a tiny sample of radioactive material, a Geiger counter, a small hammer, and a sealed vial of lethal hydrocyanic acid. The apparatus was set up so that if a single radioactive atom decayed within 1 hour, the Geiger counter would register the event, release the hammer, shatter the glass vial, and kill the cat. If no decay occurred, the cat would remain unharmed. In popular culture, this thought experiment is often presented as a mysterious claim that quantum physics allows real cats to exist in a strange, ghostly state of being simultaneously alive and dead. That was not Schrödinger's point. In fact, it was the exact opposite of what he was arguing. Schrödinger constructed the story of the cat as a reductio ad absurdum, a sharp counter-argument designed to demonstrate how bizarre and incomplete the standard quantum formalism becomes when you scale microscopic superpositions up to everyday macroscopic objects without providing a mechanism for measurement. He was pointing out that if the standard wave equation is applied universally without modification, it forces us to accept that the entire chamber, vial, hammer, atom, and cat enters an entangled superposition of a dead cat with a shattered vial and a live cat with an intact vial. For Schrödinger, a theory that forced such a conclusion without explanation was clearly missing a vital piece of physical reality. In 1961, Eugene Wigner pushed this paradox even further with a scenario known as Wigner's friend. Imagine a scientist, Wigner's friend, sealed inside an isolated laboratory, performing a quantum measurement on a single particle. The friend looks at the detector, sees a single light flash, and records a definite result in a notebook. For the friend inside the room, a concrete physical event has definitely occurred. The outcome is fixed and recorded. And if you happen to fall asleep right here, that is completely fine. The universe will take care of itself while you rest. Now consider Wigner standing outside the sealed, perfectly insulated laboratory. Because Wigner remains outside, he has not interacted with the instrument or his friend. If Wigner uses standard quantum mechanics to describe the entire laboratory, he must treat the room, the equipment, the notebook, and his friend as a single, uncollapsed quantum system. From Wigner's perspective outside, his friend remains in a superposition of having seen the red light and having seen the blue light. Here, two observers, both using valid quantum mechanics, arrive at contradictory descriptions of reality. The friend inside insists that a definite outcome has already taken place. Wigner outside maintains that the entire room remains in a superposition of possibilities. The formalism provides no clear answer as to who is correct or whether a single objective event has actually occurred. It is vital to emphasize that the measurement problem is not a technical limitation caused by clumsy or imprecise laboratory instruments. Building more sensitive detectors, reducing electronic noise, or shielding experiments from vibrations does not resolve the issue. High-precision instruments allow us to measure smaller signals with greater accuracy, but they operate under the exact same quantum rules. The problem is not that our measurements are noisy. The problem is that our fundamental equations do not contain a definition for what a measurement actually is. This was the core of a fierce objection raised by the physicist John Stuart Bell. Bell strongly criticized the standard presentation of quantum mechanics for relying on vague, unexamined words like Magianet, observation, or apparatus in its fundamental postulates. He argued that a fundamental theory of physics should not divide the cosmos into two arbitrary realms, a microscopic world governed by quantum waves and a macroscopic world governed by special measuring devices. Physics, Bell insisted, should be about the physical world itself, not about our human laboratory procedures. A complete theory must specify precisely what physical processes occur, by what mechanisms they operate, and under what exact physical conditions a definite event takes place. Faced with the measurement problem, physicists are forced to choose between three broad paths forward. First, one can accept that measurement is a special fundamental event, introducing a rule that causes the wave function to collapse whenever an observation occurs. Second, one can insist that the smooth Schrödinger equation never breaks, accepting that all branches of the superposition continue to exist in a vast, ever-branching reality or a relational web of information. Third, one can modify the underlying dynamical laws of physics, introducing new physical mechanisms, such as hidden guiding waves or spontaneous physical collapses, that force a single outcome to emerge automatically in the macroscopic world. Every interpretation of quantum mechanics ever proposed is an attempt to walk one of these three paths. Each path offers a way to restore clarity to the machine, and each path demands a profound sacrifice in return. To understand how the founding fathers of quantum theory chose to answer this challenge, we must look to the first and oldest of these paths, a school of thought that bears the name of a European city. When textbook writers look back at the origins of quantum theory, they often present the Copenhagen interpretation as a single, polished doctrine, a clear set of answers carved into stone during the 1920s. The reality was much more human and far more complex. Copenhagen was not a single, rigid philosophy. It was a loose family of related ideas that coalesced around Niels Bohr's Institute for Theoretical Physics in the quiet Danish capital. The pioneers who gathered there, Niels Bohr, Werner Heisenberg, Max Born, Wolfgang Pauli, and others, were united by a single, revolutionary conviction. The intuitive concepts of classical physics could not be applied directly to the atomic realm. Beyond that shared conviction, however, they were far less unified on what should take classical physics' place. Niels Bohr's deep philosophical reflections were not identical to Werner Heisenberg's mathematical pragmatism. Max Born focused strictly on probability amplitudes, while Wolfgang Pauli occasionally made more adventurous philosophical remarks. In later decades, textbook authors smoothed out these internal shades of meaning into a standardized textbook Copenhagen model, a simplified version that perhaps none of the original founders would have signed in every detail. At the center of Bohr's thinking was the principle of complementarity. Bohr recognized that quantum objects display physical properties that appear contradictory when viewed through a classical lens. In one experimental arrangement, light and matter behave as continuous, spreading waves, creating intricate patterns of interference. In a different experimental arrangement, those same entities act as discrete, localized particles, striking a detector screen at single, isolated points. Bohr argued that wave-like behavior and particle-like behavior are not mutually exclusive contradictions. They are complementary aspects of a single quantum reality. The experimental conditions required to observe wave properties naturally prevent the observation of particle properties, and the conditions needed to measure particle behavior eliminate the wave aspects. You can choose which question to ask nature, but you cannot ask both questions at the exact same instant. Consider the classic double-slit experiment. If you set up a barrier with two narrow slits and allow a stream of electrons to pass through without attempting to track which slit each electron enters, an interference pattern emerges on the far detector screen. The wave function navigates both slits simultaneously as a wave. If you then modify the apparatus, placing a light source near the slits to record which path each electron takes, the interference pattern vanishes completely. The particles now pile up in two simple, separate bands behind the slits. This transformation does not occur because the electron is somehow shy or aware of human presence. It happens because the entire experimental arrangement has changed. By introducing a physical mechanism capable of extracting path information, you have altered the physical interactions taking place. For Bohr, it was meaningless to talk about the properties of an electron in isolation. Physical statements, only make sense when tied to the complete experimental setup used to measure them. Because human beings are macroscopic creatures living in a macroscopic world, Bohr insisted that all experimental arrangements must be described using the unambiguous vocabulary of classical physics. Even though a measuring instrument is ultimately made of atoms governed by quantum mechanics, we must describe its operation using everyday classical terms: position, time, pointer directions, and detector clicks. We must be able to tell another scientist exactly how the apparatus was constructed and what concrete result was observed. A physical measurement must leave a permanent, unambiguous record in the macroscopic world. This requirement led Heisenberg to introduce the concept of the Heisenberg cut, the imaginary line dividing the quantum system from the classical measuring device. In a quantum calculation, everything on the microscopic side of the cut is treated using wave functions and linear equations. Everything on the macroscopic side of the cut is treated as a classical object with definite properties. What makes the Heisenberg cut fascinating and deeply troubling is that the cut is movable. If you are analyzing an experiment, you can place the cut right between an electron and a detector screen, or you can push the cut further back, treating both the electron and the detector screen as a single quantum system, and placing the cut at the eye of the human observer. Remarkably, wherever you choose to place the cut, the final mathematical prediction for the observable outcome remains exactly the same. This mobility is extraordinarily convenient for practical calculations. But it raises an uncomfortable question: is the Heisenberg cut a real, physical boundary in nature, or is it merely an arbitrary choice made by the person doing the calculation? The Copenhagen tradition never offered a single, universally accepted answer. Max Born added another essential pillar to the Copenhagen family by reinterpreting Schrödinger's wave equation. Born argued that the wave function does not describe a continuous physical cloud of matter spreading through space. It provides probability amplitudes, mathematical tools used to calculate the likelihood of observing a particle at a specific location when a measurement occurs. Under this view, the absence of a continuous classical trajectory, a smooth path tracking an electron at every microsecond, is not a temporary failure of our laboratory equipment. It is a sign that demanding a continuous trajectory between measurements is a question that has no physical meaning in that experimental context. It is here that we must address one of the most persistent myths surrounding the Copenhagen interpretation: the claim that Copenhagen asserts that human consciousness creates physical reality. This popular claim is both too strong and far too simplistic. It is true that in the early days of quantum mechanics, a few physicists speculated about the role of human awareness and observer knowledge, which allowed the misunderstanding to take root. But the central consensus of the Copenhagen group was quite different. Their focus was not on human consciousness, but on the physical interaction between a quantum system and a macroscopic experimental arrangement, an interaction that creates an irreversible physical record. A conscious human mind does not need to stand in the laboratory, staring at a detector for a measurement to take place. A photographic plate inside an automated camera will record the impact of a single photon, leaving a permanent chemical trace on the emulsion. That photographic plate retains its mark in total darkness long before any human eye opens the door to inspect it. The measurement occurred when the irreversible physical record was created, not when a human mind became aware of it. The strength of the Copenhagen interpretation lies in its profound intellectual restraint. Copenhagen physicists refuse to speculate about what happens in the dark between measurements. They stayed close to actual laboratory practice, reminding us that science is built on observable phenomena rather than unprovable microscopic pictures. They taught us that every statement about a quantum particle must be understood within the specific experimental context in which it was observed. Yet the weaknesses of Copenhagen sprout from the exact same soil. By treating measurement as a fundamental postulate, Copenhagen leaves the word measurement undefined. It relies on a fuzzy, movable boundary between the quantum and classical worlds without providing a physical mechanism for where that boundary lies. It uses wavefunction collapse as an effective calculation rule, but fails to provide a physical explanation for how or why that collapse occurs. And it leaves us perpetually uncertain whether the wave function describes nature itself, our knowledge of nature, or merely our expectations for a specific laboratory experiment. The Copenhagen interpretation taught us to speak with extraordinary discipline about what physical experiments reveal. It failed to tell us what reality is doing when no experiment is forcing a choice. And for some of the greatest minds in physics, that silence was completely unacceptable. Chief among them was a man who refused to believe that nature's deepest secrets could be reduced to a set of laboratory rules, a man named Albert Einstein. Albert Einstein did not believe that quantum mechanics was wrong. That is one of the most widespread misconceptions in the history of science. Einstein was one of the theory's earliest architects. In 1905, it was Einstein who proposed that light was quantized into photon packets, a breakthrough that earned him the Nobel Prize. He understood the mathematical machinery of quantum mechanics as deeply as anyone alive, and he used it throughout his career. What troubled Einstein was not that the calculations were inaccurate. What troubled him was the claim that quantum mechanics provided a complete description of physical reality. To Einstein, the probabilistic nature of quantum theory felt like an incomplete summary. Consider a weather report that predicts a 60% chance of rain in your city tomorrow. The forecast might be accurate, but no meteorologist claims that the forecast is a complete description of the atmosphere. The forecast uses probability because we do not track every molecule of air, every temperature gradient, and every water droplet. Classical thermodynamics describes heat and pressure with tremendous accuracy without listing the position of every individual atom. Einstein suspected that quantum probabilities were operating in much the same way. He believed that underneath the probabilistic wave functions laid a deeper, more deterministic reality, a set of pre-existing physical properties that quantum theory simply failed to capture. Throughout the late 1920s and 1930s, at the famous Solvay conferences in Brussels, Einstein engaged in a series of legendary debates with Niels Bohr. Einstein would arrive at breakfast with a newly invented thought experiment involving shuttered boxes, hanging scales, light pulses, and precise clocks, designed to demonstrate that a particle's energy and time of departure could be measured simultaneously, violating the uncertainty principle. Bohr would spend the day analyzing the entire experimental arrangement, often showing that Einstein had forgotten to account for the gravitational recoil of the box itself. By evening, Bohr would demonstrate that the uncertainty principle held firm. These Solvay debates were not mere intellectual games. They exposed a fundamental clash between two incompatible visions of what physics should be. Bohr believed that science could only speak about the results of specific, recorded experiments. Einstein insisted that science must describe an objective physical world that exists independent of our measurements. In 1935, Einstein, along with two younger colleagues, Boris Podolsky and Nathan Rosen, published a paper that turned this philosophical debate into a precise logical challenge. It became known as the EPR paper. The EPR argument imagined two quantum particles that interact and then drift far apart in opposite directions. Because the two particles interacted, their properties become linked. Under quantum mechanics, if you measure the position of particle A, you can instantly infer the position of particle B with absolute certainty without touching particle B. If you choose instead to measure the momentum of particle A, you can infer the momentum of particle B with absolute certainty. EPR introduced a simple criterion for physical reality. If you can predict the value of a physical quantity with certainty without disturbing the system in any way, then there must exist an element of physical reality corresponding to that quantity. The key to their argument was locality. Because particle B was separated by a vast distance from particle A measurement performed on particle A could not possibly cause an instantaneous physical disturbance at particle B. Therefore, particle B must have already possessed a definite position and a definite momentum before anyone measured particle A. Since standard quantum mechanics refuses to assign simultaneous, definite values to both position and momentum, Einstein, Podolsky, and Rosen concluded that the quantum wave function was incomplete. There had to be hidden variables, pre-existing physical properties, that the standard theory was missing. Niels Bohr published a response to EPR later that same year. Bohr did not argue that a physical signal traveled instantaneously from particle A to particle B. Instead, he challenged the very definition of EPR's element of reality. Bohr argued that the physical meaning of any property depends entirely on the complete experimental setup. The apparatus needed to measure position is mutually exclusive with the apparatus needed to measure momentum. You cannot combine inferences drawn from two incompatible experimental arrangements as if they revealed a single pre-existing set of classical traits. Around the same time, Erwin Schrödinger gave this strange quantum link a name that would endure: entanglement. Schrödinger called entanglement the characteristic trait of quantum mechanics, the precise feature that forces the theory to depart from classical thought. Einstein was unimpressed. He famously dismissed this distant connection as spukhafte Fernwirkung, ghostly action at a distance. For Einstein, the core issue was separability. If two objects are separated in space, they must have independent physical identities. If measuring one instantly alters the physical reality of the other across light years, then local physics collapses. For nearly 30 years, the debate remained stuck in a philosophical deadlock. Bohr and Einstein both passed away without seeing the dispute resolved. Physicists on both sides agreed on every calculation, so the question of whether hidden variables existed seemed beyond the reach of experimental science. It was regarded as a topic for late-night philosophical discussions, not laboratory physics. That changed in 1964, when a quiet Irish physicist named John Stuart Bell published a paper that reshaped the foundation of science. Bell asked a simple question: what if we stop arguing about philosophy and test the assumptions mathematically? Bell proved a remarkable theorem. He showed that any theory at all that combines two natural assumptions, locality, meaning no influence travels faster than light, and realism, meaning physical properties exist prior to measurement, must obey strict statistical limits. These mathematical bounds became known as Bell inequalities. Bell then demonstrated that standard quantum mechanics predicts that entangled particles will violate these inequalities. It is vital to understand what a Bell inequality actually measures. A Bell test does not look at a single pair of particles and declare it strange. A single measurement on one pair yields an ordinary random result that looks completely normal. A Bell inequality is a statement about statistics accumulated across thousands of trials. Imagine two experimenters operating independent detectors separated by a wide distance. For each incoming pair of entangled particles, each experimenter randomly chooses one of several detector angle settings. When they record their results over thousands of runs, they compare how often their readings match or mismatch across different angle combinations. Bell proved that if the particles carried pre-existing, local hidden instructions, like a pair of matching shoes placed into two sealed boxes, their correlation rates could never exceed a specific mathematical limit. But if quantum mechanics was correct, the entangled particles would show a degree of statistical coordination that exceeded any possible local hidden instruction set. Bell had transformed a 50-year philosophical debate into a measurable physical difference. To bring Bell's theorem into real laboratories, 4 physicists, John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, formulated a practical version known as the CHSH inequality. In the early 1970s, Stuart Friedman and John Clauser built the first experimental test at the University of California, Berkeley, using pairs of entangled photons. Their results delivered a clear answer. The data violated that inequality, agreeing with quantum mechanics and contradicting the local hidden variable predictions. Yet early experiments left room for doubt, known as loopholes. The first was the locality loophole. If the detector angles were set before the photons left the source, the particles might somehow communicate via ordinary light-speed signals before being measured. In 1982, Alain Aspect, Jean Dalibard, and Gérard Roger in Orsay, France, closed this loophole by inventing a mechanism that switched the detector orientations while the photons were actively in flight. The choice of angle was made so late that no signal traveling at the speed of light could pass between the detectors in time to influence the outcome. Still, a second major loophole remained: the detection loophole. Early detectors only registered a small fraction of the emitted photons, leaving open the slight possibility that the uncollected particles carried different statistics. That brings us back to the night where our story began. In 2015, 80 years after the EPR paper was published, 3 independent research groups set out to close both major loopholes simultaneously. One team operated at the University of Vienna, another at the National Institute of Standards and Technology in Boulder, Colorado, and a third at the Delft University of Technology in the Netherlands. Recall that quiet Dutch night across the campus in Delft. 2 synthetic diamonds sat in separate basements, separated by 1.3 kilometers of optical fiber cable. Embedded inside each diamond was a single electron spin. The researchers entangled those 2 distant electron spins, selected their detector angles using high-speed random number generators while the measurement was underway, and read the spins with near-perfect efficiency. That experiment in 2015, along with the tests in Vienna and Boulder, produced a loophole-free Bell test. The data was definitive. The recorded correlations violated Bell's inequality with staggering statistical certainty. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for these landmark experiments with entangled photons, establishing the violation of Bell inequalities and pioneering the field of quantum information science. Yet here we must exercise the utmost intellectual discipline and state precisely what these experiments proved and what they did not prove. Loophole-free Bell tests prove that nature cannot be described by local hidden variable theories that satisfy the standard assumptions of Bell's theorem. Local realism, as Einstein envisioned it, is dead. However, Bell tests do not prove that particles lack all definite properties prior to measurement. They do not rule out all hidden variable theories. For example, de Broglie-Bohm pilot wave theory maintains that particles have exact pre-existing positions at all times. Pilot wave theory survives Bell's theorem precisely because it is explicitly non-local. It openly accepts that an action here instantly alters the guiding wave everywhere else. Nor do Bell tests select a winning interpretation among the survivors. They do not prove that Copenhagen is correct, nor do they prove that many worlds is true. They simply eliminate one specific, comfortable family of local explanations, leaving the remaining interpretations to deal with the consequences. Finally, it is essential to understand the no-signaling theorem. Although entangled particles exhibit statistical correlations that defy local classical explanation, these correlations cannot be used to send controllable messages faster than light. When an experimenter at one end measures their particle, they observe a completely random sequence of results. They cannot force their particle to land on a specific outcome to send a code. The spooky correlation only reveals itself later, when both experimenters bring their recorded ledgers together and compare them side by side using ordinary light-speed communication. Quantum entanglement is a deep structural feature of reality, but it is not a faster-than-light telephone. The equations agree, the stories do not. Bell's theorem proved that the universe cannot be both local and classical. If we insist that quantum states evolve smoothly everywhere without breaking, we are forced to ask why the macroscopic world appears so remarkably solid, localized, and stable to our everyday senses. John Bell showed us that the quantum world refuses to be confined to local, classical rules. The invisible connections between entangled particles stretch across space, openly ignoring our intuitive demands for separability. The microscopic realm is undeniably, demonstrably strange. And yet, if you consider the quiet room you are resting in right now, it does not feel strange at all. Your desk remains solidly in one place, its edges sharply defined. The dials on a clock show steady, unambiguous numbers. A speck of dust floating in the air does not smear across the room in conflicting positions simultaneously. A glass of water resting on the nightstand does not split into a ghostly set of alternative glasses just because no one happens to be paying attention to it. The macroscopic world feels reassuringly solid. It obeys the comfortable, predictable rules of classical physics that Isaac Newton wrote down centuries ago. This is the great paradox that follows Bell's theorem. If everything in the universe is ultimately made of quantum particles, and if all those particles obey the relentless mathematics of the Schrödinger equation, why does the everyday world seem so incredibly normal? How does the quantum strangeness disappear before we can perceive it? For many decades, physicists thought the answer lay somewhere in the mysterious act of measurement itself. They suspected it involved a conscious observer, or perhaps a sudden, unexplained collapse of the physical state. But in the 1970s, a German physicist named Heinz-Dieter Zeh realized that the field had been ignoring a massive, ubiquitous presence. That presence was the environment. Before Zeh, the environment was mostly considered a nuisance in theoretical physics. It was treated as a messy puddle of noise that ruined delicate laboratory experiments, something to be isolated, pumped out, and shielded against. Zeh recognized that the environment was not just a source of errors. It was an essential, active participant in the dynamics of reality. To understand Zeh's insight, we must remember a crucial fact about the universe. Almost nothing in nature is perfectly isolated. Deep in a specialized vacuum chamber, shielded by thick lead walls and cooled to near absolute zero, a physicist might manage to keep a single ion isolated for a few precious fractions of a second. But out here, in the messy, warm, everyday world, isolation is entirely impossible. A particle of matter is constantly, relentlessly bombarded. A stray photon of ambient light strikes it. A wandering air molecule bumps into it. A faint pulse of thermal radiation escapes from its surface. Every single time one of these microscopic collisions occurs, the quantum state of the particle interacts with the state of the environmental intruder. And when they interact, according to the strict rules of the mathematical machine we discussed earlier, they become entangled. This process is known as decoherence. It is vital to state clearly that decoherence is not a replacement for quantum mechanics. It is not a new theory. It is the direct consequence of taking standard quantum mechanics seriously and applying it carefully to systems that cannot be kept in a pristine, isolated box. When an environmental particle, say, a single photon of light, bounces off an object that is suspended in a quantum superposition, that photon carries away information about the object's position. In a very real sense, the environment effectively measures the object. Because the environment is vast and chaotic, comprised of trillions upon trillions of particles, this entanglement spreads like a contagion. The information about the superposition leaks out into the surrounding room, dispersing into the air currents, the walls, and the background thermal glow of the universe. As this information leaks away, the delicate phase relationships that hold a quantum superposition together are scrambled. In the mathematical machinery of quantum mechanics, this scrambling is described using something called a reduced density matrix. When a system is perfectly isolated, this matrix contains off-diagonal terms, mathematical elements that represent the pristine interference between different possible states. These off-diagonal terms are the absolute signature of quantum weirdness. They are what allow a particle to pass through two slits at once and form a wave-like interference pattern on a screen. But when the environment begins its relentless bombardment, it introduces random, fluctuating phase shifts. The countless particles of the environment act like an ocean of static, washing over the delicate quantum state. In the reduced density matrix, those off-diagonal interference terms rapidly shrink away, approaching absolute zero. The system loses its ability to interfere with itself. It loses its quantum coherence. From the limited perspective of anyone measuring only the object itself, and ignoring the trillions of environmental particles scattered across the room, the object acts as if it has collapsed. It behaves exactly like a classical mixture of possibilities, like a coin resting under a cupped hand, definitively heads or definitively tails. We just do not know which one yet. What is truly staggering about decoherence is the speed at which it happens. Consider a tiny speck of dust, perhaps 10 micrometers in diameter, floating in the air of a quiet room at normal room temperature. Now imagine we somehow manage to place that single dust grain into a quantum superposition, separating its two possible positions by a microscopic distance equal to its own width, just 10 micrometers. How long would it take for the surrounding air molecules and thermal photons to interact with that dust grain, entangle with it, and wash away its quantum coherence? It would not take a second. It would not take a millionth of a second. The loss of coherence would occur in a timescale so brief it defies human intuition. The off-diagonal terms in the density matrix would vanish in a time much shorter than it takes light to cross the tiny dust grain itself. Macroscopic objects do not just decohere. They decohere almost instantly. The classical world is forged in the relentless, rapid-fire measurement executed by the environment. And if you drift off here, letting the complexity of the density matrix fade into the background, that is perfectly all right. The math will still be here. What matters is the image of the world constantly measuring itself, locking its own objects into place. In the 1980s, a physicist named Wojciech Zurek developed the theory of decoherence even further, answering another profound question. The environment does not just destroy quantum superpositions, it also selects. Out of the infinite number of possible bases in the Hilbert space, the vast mathematical landscape of all quantum possibilities, why do we always find objects with definite positions? Why do we not find everyday objects in a state of definite momentum, smeared out across the entire room? Zurek introduced the concept of pointer states and a process called Einselection, short for environment-induced superselection. The environment is not a neutral, passive observer. It interacts with objects in very specific physical ways, primarily through distance and position. When an air molecule bounces off a dust grain, the strength and timing of that interaction depends entirely on exactly where the dust grain is located. Therefore, the environment preferentially measures position. Einselection means that the environment is deeply hostile to most quantum states. It ruthlessly destroys superpositions of position, but it is tolerant of a select few states. The pointer states. These are the robust classical states that can withstand the constant battering of environmental observation without being fundamentally changed. Because of the nature of physical interactions, pointer states are almost always states of definite position. This is why things always seem to be somewhere. Zurek later expanded this into a broader framework he called quantum Darwinism. The idea is that information about an object is copied redundantly into the environment, and only the fittest information survives and spreads. When our dust grain is illuminated by the ambient light in the room, it scatters billions of photons in all directions. Every single one of those scattered photons carries a tiny replica of the information about where the dust grain is located. Because the information is copied so many millions of times, multiple observers can intercept entirely different batches of photons. You can intercept photons from the left side of the room, while someone else intercepts photons from the right, and you will both agree on exactly where the grain is. The redundant spreading of this information creates the illusion of classical objectivity. It creates a shared reality that we can all agree upon. This provides a beautiful, cohesive explanation for why the macroscopic world acts the way it does. It bridges the microscopic rules of the Schrödinger equation with the solid, classical tables and chairs of our everyday experience. But here we must be extremely careful. We must state exactly what decoherence accomplishes and exactly what it leaves unanswered. Decoherence perfectly explains why we do not observe macroscopic interference. It explains why a cat in a box does not act alive and dead at the same time, because the environment inside the box measures the cat instantly. It explains why the probabilities we calculate in quantum mechanics eventually behave just like the classical probabilities of a shuffled deck of cards. What decoherence does not do is solve the measurement problem. Decoherence does not collapse the overall wave function. It absolutely does not select a single, actual outcome from the array of possibilities to become the one true reality. We know it does not do this because the mathematics of decoherence relies entirely on the smooth, unbroken evolution of the Schrödinger equation. When the dust grain entangles with the environment, the total wave function of the combined system, the dust grain plus the air molecules plus the photons, is still in a massive, sprawling superposition. The off-diagonal interference terms in the density matrix disappear only when we mathematically trace out the environment, deliberately ignoring it, because we simply cannot track every scattered photon in the room. But in the full, unedited reality of the universal wave function, those terms are still there. The superposition has not vanished. It has merely become so complex and so hopelessly entangled with the rest of the universe that it is practically impossible to reverse. Decoherence explains why the different branches of a quantum superposition no longer feel each other. It explains why they can no longer interfere. It does not explain why only one branch is experienced by us. We have never proven that the other branches cease to exist. We have also never confirmed that they must remain, and those two statements are not the same thing. If decoherence only hides the superpositions from our experience, rather than erasing them from reality, then perhaps those alternative outcomes are still out there, all of them, surviving in parallel, completely disconnected from our own. And that possibility requires us to face directly a person who dared to say exactly that. A person who wrote a quiet thesis in the 1950s that would wait decades to be heard. A story we will follow as this night continues. At the end of the previous chapter, we arrived at a staggering possibility. If decoherence merely hides quantum superpositions from our experience, rather than erasing them from reality, then perhaps those alternative outcomes are still out there. In the 1950s, a young graduate student named Hugh Everett proposed exactly this. Working at Princeton University, he wrote a quiet thesis that would be largely ignored for decades before fundamentally dividing the physics community. His solution was the most radical idea in the history of quantum mechanics, yet it was achieved by doing less, not more. Everett proposed that we should not add anything new to the equations. Instead, we should drop something. We should drop the idea of the collapse. In Everett's view, the universal wave function evolves continuously according to the Schrödinger equation, forever, without interruption. Every single possible outcome of a quantum event continues to exist. They simply exist in separate branches that have decohered from one another. This flows naturally from what we have already discussed. Decoherence has done the heavy lifting. The branches do not require an additional mysterious law of nature to create them. They emerge automatically because interactions with the environment make the different physical records practically incapable of interfering with one another anymore. The branches simply stop feeling each other, drifting apart into separate, non-communicating realities. To be perfectly fair to this interpretation, its true appeal is its austere elegance. There is a single law applied everywhere, from the smallest atom to the entire cosmos. There are no special observers whose consciousness is required to make reality solid. There is no vague, shifting boundary between the quantum world and the classical world. There is no mystical moment when a ghostly possibility suddenly turns into a hard reality. It is the most economical interpretation of the physical laws ever devised. But the price of this economy lies elsewhere. The problem lies with probability. If you are drifting off to sleep as we speak, let the details wash over you. But if you are listening closely, this is the very heart of the mystery. This is where the many worlds interpretation faces its greatest challenge. If every possible outcome actually occurs, what does it mean to say that one outcome is more probable than another? In our everyday lives, probability is a measure of uncertainty about what will happen. When you flip a coin, it will land heads or it will land tails. Only one face will become reality. Your uncertainty stems from the fact that you do not know which single future will materialize. But in Everett's universe, both faces become reality. The coin lands heads in one branch and it lands tails in another. You split into two observers, one recording heads, the other recording tails. If you know with absolute certainty that both futures will happen, the question about what the chances are can no longer be asked in the old way. The simplest idea might be to just count the branches. If there are two branches, maybe the probability is 1/2 for each. But that strategy fails completely, and we must understand why. Decoherence does not generate a neat, discrete, countable set of isolated worlds. Branching is continuous. It is approximate. It is extraordinarily complex. When a laboratory result happens, it entangles with an air molecule, then a photon, then a microscopic vibration in the floorboards, then a computer memory, and countless other microscopic details. Each interaction creates further differentiation, splitting the state into an endlessly complex web of possibilities. There is no fundamental rule in nature that dictates exactly how many branches there are. If you group the mathematics of the wave function slightly differently, you might change the number of branches you count without changing the underlying physics one bit. A count that depends entirely on how we choose to write down the description cannot be the foundation for physical probability. Because they cannot count branches, physicists who study Everett's theory use branch weights instead. A branch with a larger quantum amplitude carries a larger weight. The relevant quantity is the squared magnitude of the amplitude, which perfectly matches the Born rule, the standard formula used to predict quantum probabilities. But defining a weight is not the same as explaining it. It simply renames the problem. Why should a mathematical weight in a deterministic equation behave like a probability in our experience? Physicists have developed 3 main avenues to justify this, each fascinating and each facing its own counterarguments. The first is the decision theory approach, pioneered by David Deutsch and David Wallace. They ask us to consider a perfectly rational agent who must make a choice before a quantum split. The agent knows that multiple future versions of themselves will soon exist, and each version will experience a different outcome. Deutsch and Wallace argue mathematically that a rational agent should value those future branches exactly according to their Born weights. It is a brilliant argument, but the counter-argument is equally sharp. Does this approach genuinely derive probability from the physics, or has it cleverly smuggled the crucial features of probability into its assumptions about what constitutes rational behavior? The second avenue comes from Wojciech Zurek, the same physicist who developed quantum Darwinism. He calls his approach invariance. Invariance relies on the profound symmetry of entangled quantum states. Zurek argues that when two quantum choices have equal amplitudes, they can be mathematically swapped using specific symmetries without changing the overall state. Because the state itself does not care which is which, an observer should assign them equal probability. More complex, unequal states can then be conceptually divided into combinations of these balanced choices. Again, it is an elegant mathematical deduction. And again, some critics argue that the method subtly assumes the very notion of equal likelihood that it is trying to prove. The third avenue involves something called self-locating uncertainty. Imagine waking up in one of many identical rooms in a vast hotel. You know that every room exists. You know that they are all real, physical places. But when you first awaken, before you open the door to hear the sounds from the hallway, you do not yet know which specific room you are currently in. The uncertainty is not about whether the branches exist. The uncertainty is entirely about which perspective will be experienced by the version of you that is asking the question. The counter-argument here strikes at the core concept of personal identity. Once every future version of you exists, is there truly a physical fact of the matter about who the pre-branch person will become? Every single successor follows equally and continuously from the prior person. Asking which one you will turn out to be might simply be a grammatical error, a failure of language to handle a branching reality. To answer these persistent doubts, Everettians point to the typical observer argument. Imagine performing the exact same quantum measurement thousands of times in a row. According to the mathematics, the universal wavefunction develops branches containing every single possible sequence of outcomes. This means there are branches containing bizarre, highly improbable sequences. There are branches where a result that should happen only 1% of the time appears almost every single time you measure it, defying all common sense. Those anomalous branches do not vanish. They are real, but their total mathematical weight is extraordinarily, unimaginably small. Meanwhile, nearly the entire weight of the universal wave function lies in the branches containing typical observers who record long-run frequencies that perfectly match the standard quantum predictions. The vast majority of the stuff of reality experiences the normal laws of probability, while the bizarre anomalies are starved of mathematical weight. Here we must act as honest brokers. The problem of probability does not uniquely belong to many worlds. The Copenhagen family of interpretations must accept that probability is either a fundamental, unexplainable randomness injected into the universe or simply a measure of our own incomplete knowledge. Objective collapse theories must explain exactly why their physical collapse mechanism happens to perfectly obey the Born rule. The pilot wave theory is completely deterministic, but it must invent a justification for why particles start off with a specific distribution of initial positions. Every interpretation struggles with probability. Many worlds merely makes the problem impossible to ignore because it refuses to erase anything. Hugh Everett managed to retain every predictive capability of quantum theory without adding a single new law. He has also never completely explained why you should expect one experience over another. And those two statements are not the same thing. If you are unwilling to pay the price of infinite branches and fragile probabilities, you must turn elsewhere. The next two schools of thought go in the completely opposite direction. They hold fiercely to a single, definite world, and they pay for that luxury in two very different ways. If the infinite branching of many worlds feels too heavy a price to pay, you must turn elsewhere. The next two schools of thought go in the completely opposite direction. They both reject the endless splitting of realities. They both fiercely defend a single, definite world, where experiments yield only one true outcome. But they pay for that luxury in two entirely different ways. The first approach began in 1927 at the famous Solvay conference in Brussels. A French physicist named Louis de Broglie proposed a startling idea. Perhaps quantum particles are guided by an accompanying wave. At the time, the idea found very few supporters. The Copenhagen tradition was rising to dominance, and there were serious, technical objections raised against any attempt to invent hidden variables. De Broglie's idea was quietly shelved. Then, in 1952, David Bohm resurrected it. Bohm reconstructed the idea into a complete, rigorous hidden variable theory that flawlessly reproduced all the predictions of non-relativistic quantum mechanics. Today, it is known as de Broglie-Bohm theory, Bohmian mechanics, or simply pilot wave theory. The physical description it offers is unusually clear, almost comforting in its concreteness. In pilot wave theory, there is a wave function, and it evolves continuously according to the Schrödinger equation, just as it always does. But there are also particles, and every single particle possesses a definite, exact position at every single moment in time. The wave function does not merely describe our ignorance of those positions. It physically guides their motion. The velocity of every particle is precisely determined by the wave function and by the positions of all the other particles in the system. If you know the initial wave function and the exact initial arrangement of the particles, their future motion is completely deterministic. Consider the famous double-slit experiment, the very heart of quantum weirdness. Pilot wave theory explains it cleanly. In this view, the physical particle goes through one slit and only one slit. It always has a definite position, and it follows a continuous, unbroken path, but the guiding wave goes through both slits. The two parts of the wave spread out, overlap, and interfere with one another. This complex, rippling structure then steers the particle, guiding it towards certain regions of the detector and actively steering it away from others. Each particle arrives and leaves a single mark. As you send more particles, the familiar interference pattern builds up. The particle never needs to split in two, and it never needs to somehow know whether the other slit is open or closed. It just surfs the guiding wave. Measurement in this theory is refreshingly straightforward. The measuring apparatus always possesses a real physical configuration of particles. A dial points in one specific direction. A detector records one specific click. The particles in the brain of the observer are arranged in one actual state. A single outcome is experienced, and no fundamental collapse of the wave function is ever required. The other mathematical components of the wave function, the branches representing the outcomes that did not happen, still exist mathematically. Physicists call them empty wave packets because they contain no actual particles. Once decoherence separates them sufficiently from the actual outcome, they stop affecting the real configuration of particles in any observable way. They simply drift away as mathematical ghosts. But if the underlying motion is completely deterministic, why do quantum outcomes seem random? The answer is quantum equilibrium. If the initial positions of the particles in a vast ensemble are distributed according to the standard Born rule, the guiding dynamics perfectly preserve that distribution as time moves forward. An observer never knows the exact initial configuration of a system, so the individual results remain entirely unpredictable to them, even though the hidden gears of the universe are turning with absolute certainty. But this clarity comes at a severe price. In pilot wave theory, if two particles are entangled, the velocity of one particle can depend instantly on the exact position of the other. No matter how far apart they are, the velocity depends on the joint wave function encompassing both. The theory is explicitly, unapologetically non-local. This is not an accidental inconvenience that can be quietly, mathematically adjusted. John Stuart Bell's theorem proved that any hidden variable theory capable of reproducing all quantum correlations cannot possibly maintain locality in the classical sense. Pilot wave theory survives Bell's theorem precisely because it does not even try to be local. It openly embraces the spooky action. And yet, because of quantum equilibrium, observers cannot use this non-local connection to send messages faster than light. They still only experience a sequence of random results, keeping the cosmic speed limit intact. If you are drifting off here, lulled by the deterministic clockwork, that is perfectly fine. The details of the hidden gears will keep turning without you. There are remaining challenges, of course. The wave function for many particles must live in a highly abstract, multidimensional configuration space, which strains the intuition. The theory seems to unfairly elevate particle position above all other properties, like spin. And while extending pilot wave theory to cover quantum fields, antimatter, and relativity is possible, it is much less simple. A fully satisfactory version that sits comfortably with the structure of spacetime remains an open problem. Physicists also debate exactly why the universe would begin in a state of perfect quantum equilibrium. Yet, John Stuart Bell himself considered Bohm's theory to be incredibly important. It proved that sweeping claims declaring hidden variables impossible were simply too broad. What the experiments ruled out was not all deeper reality, but specifically local hidden variables. The second school of thought takes a more blunt approach to the problem. Instead of reinterpreting the collapse or trying to explain it away, these physicists suggest we should simply fix the equations. They argue that collapse is a real, physical process. It does not wait for a conscious observer to arrive. It does not depend on whether someone happens to be listening to a detector. It happens spontaneously, driven by additional, undiscovered laws of nature. This is the path of objective collapse theories. The most famous of these was proposed in 1986 by Giancarlo Gherardi, Alberto Rimini, and Tullio Weber, known simply as the GRW model. They started with the standard wave function, evolving smoothly according to the Schrödinger equation. Then, they added rare, spontaneous localization events. They proposed that every microscopic component has a vanishingly small probability of undergoing a sudden, spontaneous collapse. When this happens, the wave function sharply localizes around a specific region of space. The brilliance of the GRW model lies in its amplification mechanism. For a single, isolated microscopic particle, these events are incredibly rare. In the original model, the proposed rate was about 1 event per particle every 100 million years. Therefore, an isolated electron or atom can comfortably exist in a superposition long enough to show perfect interference in any laboratory experiment. But a macroscopic object, like a detector dial or a speck of dust, contains billions of microscopic components. Even though the probability for any individual particle to collapse is unimaginably tiny, the probability that some particle within the massive object will collapse is huge. And because all the particles in a solid object are entangled with one another, when one single particle spontaneously localizes, it immediately pulls the entire object to that definite position. A dial forced into a superposition of pointing left and pointing right cannot stay that way for long. Within a fraction of a second, one of its countless atoms will trigger a spontaneous localization, dragging the entire dial into a single, concrete reality. We must be careful to distinguish this from decoherence. Decoherence causes the components to lose observable interference, but the full universal wave function still contains every possibility. Objective collapse goes much further. It actually reduces the physical state, cutting away the branches until only one macroscopic choice remains. To achieve a true physical collapse, you must break the perfect linearity of the Schrödinger equation. You must also introduce genuine, fundamental randomness into nature, because the exact time and place of a collapse cannot be predicted with certainty. The theory only provides probabilities. Other physicists expanded on this idea. Philip Pearl developed continuous spontaneous localization, replacing the rare, sudden jumps with a random noise field that acts continuously, pushing systems toward definite states with an effect that grows stronger as mass increases. Later, Lajos Diosi and Roger Penrose independently proposed linking the collapse mechanism to gravity. Their reasoning was profound. A heavy object in a superposition of two different places represents two different mass distributions. According to general relativity, different mass distributions create different geometries of space-time. Penrose argued that a superposition of two significantly different spacetimes is fundamentally unstable. The greater the gravitational difference between the two states, the shorter the lifetime of the superposition, forcing the object to rapidly collapse into one location or the other. As honest brokers, we must state that while this is a fascinating physical suggestion, there is currently no complete, widely accepted mathematical theory that successfully unites gravitational collapse with quantum mechanics. But objective collapse theories possess one spectacular advantage over everything else we have discussed. They are testable. Because they actually modify the underlying dynamics of quantum mechanics, they predict tiny, measurable deviations from the standard theory. They predict an excess loss of interference that goes beyond what normal decoherence can explain. They predict anomalous heating, as the spontaneous kicks of localization add tiny amounts of energy to a system. They predict faint, spontaneous radiation. Physicists are actively hunting for these signatures right now. They are building matter wave interferometers using heavier and heavier molecules, pushing the boundary of superpositions to determine if they suddenly fail. They are designing optomechanical experiments, suspending tiny mirrors, thin membranes, and levitating nanoparticles in quantum states of motion. They are measuring ultra-cold atoms. They are placing highly sensitive detectors deep underground, shielded from cosmic rays and background noise, searching for the faint glow of unexplained radiation. They are conducting high-precision temperature measurements, monitoring whether a thoroughly isolated object slowly warms up without any normal source of heat. What are the results so far? No experiment has ever confirmed that objective collapse occurs. The results gathered to date have ruled out important regions of the parameter space. They have placed strict limits on how fast the collapse could be, how tightly it can localize a particle, and how strongly the hypothetical noise field can interact with matter. But these limits do not rule out all conceivable models. Collapse theories contain adjustable constants. An experiment might rule out one specific combination of those numbers, while leaving weaker models or slightly different mathematical structures perfectly intact. The search is therefore asymptotic, slowly tightening the net rather than delivering a single definitive blow, and the price for this testability is steep. You must add entirely new physics to the universe. You must introduce new fundamental constants, accept unexplainable randomness at the base of reality, and tolerate tiny violations of energy conservation, ensuring these modified equations remain compatible with special relativity. And quantum field theory is a massive technical hurdle. The actual physical origin of the collapsing noise remains a mystery, but most importantly, the greatest hurdle for objective collapse is that standard quantum mechanics has yet to be observed failing. We have never proven that the Schrödinger equation breaks down for large objects. We have also never confirmed that it must hold flawlessly at every scale. And those two statements are not the same thing. Objective collapse is not just telling a new philosophical story to lay over the old equations. It is placing a real, tangible scientific bet, and it is a bet that could lose. Every school of thought we have examined tonight demands a sacrifice. We give up local influences, or we give up a single reality, or we give up the purity of the Schrödinger equation. There are a few more schools of thought, quieter ones, that take a different path. They ask whether we are simply demanding something of nature that nature never possessed in the first place. We have explored the towering structures of many worlds, pilot wave, and objective collapse. But the philosophical landscape is wider than those three giants. There are a few more schools of thought, quieter ones, that take a different path. Instead of adding infinite branches or guiding waves or new physical collapses, they ask a more subtle question. They ask whether we are simply demanding something of nature that nature never possessed in the first place. The first of these is the consistent histories approach, developed by Robert Griffiths, Roland Omnes, Murray Gell-Mann, and James Hartle. Rather than asking what specific value appears at a single moment in time, this approach asks a broader question. What sequence of events, stretching across time, can be consistently described by the mathematics? The central object of study is a quantum history, a storyline where a particle is in one region early on, another region later, and finally triggers a specific detector. The problem, as always with the quantum world, is that alternative histories can interfere with one another. When they do, the mathematics forbids us from assigning a separate classical probability to each individual history. The strict rule is that you can only assign probabilities when the interference between histories has been sufficiently suppressed. Decoherence is usually the physical mechanism that provides that suppression. The great advantage of consistent histories is that it does not require an observer standing outside the equations. The particle, the detector, the notebook, and the scientist are all treated as part of one closed, mathematically described system. But there is a thorny constraint known as the single framework rule. The same physical system can often be described by different families of histories. The rule states that you absolutely cannot combine statements drawn from two incompatible families, as if they belong to a single, overarching classical description. Doing so generates artificial contradictions. This rule is remarkably close to Niels Bohr's old idea of complementarity, but it is stated in rigorous mathematical terms rather than philosophical language. This constraint is also the source of its controversy. If multiple incompatible families of histories are equally valid, which one corresponds to the actual events that people experience? Supporters argue that demanding one single, overarching framework is a classical habit we simply need to abandon. Critics argue that allowing multiple frameworks leaves far too much freedom to be a complete description of reality. The second quiet school is relational quantum mechanics, proposed by Carlo Rovelli in 1996. The core idea is that perhaps physics has been demanding an absolute state, a single description that is true from all perspectives at once, and nature simply refuses to provide one. In this view, a quantum state is not the private property of an object. It only describes the relation between one physical system and another. Consider a familiar anchor from the theory of relativity. A passenger sitting quietly on a speeding train is perfectly stationary relative to the train car. At the exact same moment, that passenger is moving rapidly relative to the ground outside. Neither description is wrong, and crucially, there is no hidden absolute velocity lurking behind both of them. Rovelli suggests that quantum states are relative in exactly the same sense. We must be careful to clarify the word observer here. In relational quantum mechanics, an observer does not require a mind. It does not need consciousness, a memory, or a white laboratory coat. Any physical system that interacts with another system plays the role of an observer. In this limited physical sense, a single atom can observe another atom. If we apply this to the thought experiment of Wigner's friend, where the friend is inside the laboratory making a measurement, and Wigner is standing outside the door, the paradox dissolves. The result of the measurement is definite relative to the friend. At the exact same time, the entire laboratory remains in a quantum superposition relative to Wigner. Neither description must be elevated to a universal, absolute view. The hard question for the relational approach is consistency. If all truths are relative, why do different observers agree with each other so reliably when they finally compare notes? Supporters argue that the deep quantum correlations naturally enforce that consistency. Critics counter that the theory speaks very clearly about individual, isolated perspectives, but struggles to explain how they weave together into a single, coherent reality. The third school is known as Cubeism, or quantum Bayesianism, developed by Christopher Fuchs, Rudiger Schack, and Carlton Caves. David Mermin became a very active and prominent supporter later on, though he must be understood as an advocate, not one of the founders. In Cubeism, the wave function is not a physical object at all. It is a mathematical expression representing a specific agent's expectations about the consequences of their own actions upon the world. In this framework, the collapse of the wave function is nothing more than the updating of beliefs when new evidence arrives. It is like updating a classical probability distribution when you learn new information. Because it is just an update of knowledge, nothing has to travel faster than light. We must emphasize that this does not reduce the world to mere personal opinion. The probabilities a cubeist calculates must obey strict, rigorous mathematical constraints. The famous Born rule is treated as a normative rule. It dictates how a rational agent absolutely must organize their judgments to remain consistent, rather than describing a mechanical gear forcing an outcome. The world is still deeply real. It still pushes back. It still delivers sharp, unpredictable experiences that the agent did not choose. The hard question for Cubeism looks deep into the past. The stars formed billions of years before any observer was born to chart them. Atoms interacted in the dark long before any laboratory was built. What is the physical world doing when no agent is around to interact with it? Furthermore, what exactly qualifies as an agent capable of holding these expectations? Must it be conscious? Can it be a machine? A simple detector? The supporters of Cubeism draw the boundaries differently, and the debate remains unsettled. We have toured the vast landscape of interpretations. You might naturally ask, why don't physicists just run an experiment to determine which one is right? The answer is empirical equivalence. Many of these interpretations yield the exact same observable predictions for every experiment we currently know how to build. An advocate for the Copenhagen interpretation, an Everettian, a pilot wave theorist, and a relational physicist can all sit down with the same initial data, calculate the outcome, and they will all predict the exact same number appearing on the detector. A detector built with an extra decimal place of precision is an impressive piece of engineering, but it does not automatically become a philosopher. It simply provides another number that all the mathematically equivalent theories will successfully predict. But empirical equivalence does not mean that all interpretations are equal in every way. Physicists and philosophers weigh these theories using other vital criteria. They evaluate explanatory clarity, mathematical simplicity, internal consistency, compatibility with relativity, the ability to connect with other fields of physics, and precision about what actually exists. An interpretation can be heavily criticized because it relies on a shifting, undefined boundary between the quantum and classical worlds. Another might be challenged because it demands an unimaginably massive, branching structure of reality. A third might be questioned because it introduces explicit non-locality, or because it says too little about the universe independent of an observer. These are real, substantive, scientific, and philosophical considerations, even when they do not yield differing numbers on a dial. And sometimes, foundational assumptions do translate into measurable constraints. This is the greatest lesson of the field. John Stuart Bell proved this in 1964 when he showed that local hidden variables carry specific statistical limits that quantum mechanics breaks. There are other profound examples. In 1967, Simon Kochen and Ernst Specker proved a theorem showing that you cannot pre-assign a definite value to every possible observable quantity while keeping those theoretical relations intact and keeping the values independent of the measurement context. The inescapable result is called contextuality. The outcome of a measurement is not always just revealing a pre-existing entry in a classical ledger. This does not mean the outcome is arbitrary, as the probabilities remain strictly bound by the mathematics, but it changes our understanding of what a property is. Similarly, the Pusey-Barrett-Rudolph theorem, which we touched on earlier, placed severe mathematical limits on the idea that the wave function is merely a representation of knowledge, provided you accept their assumption about how independent systems are prepared. These theorems prove that interpretations can be tightly squeezed by mathematics and experiment, even if they have not yet been definitively resolved. But there is a looming storm on the horizon where every single interpretation we have discussed runs into profound trouble. That storm is the intersection of quantum mechanics and gravity, leading into cosmology. Standard quantum mechanics is typically applied on a fixed, unmoving background of space and time. But general relativity teaches us that space-time itself is dynamic, bending and flexing in response to matter and energy. Merging these two pillars of physics forces a complete re-evaluation of the quantum state, the flow of time, the nature of measurement, and the meaning of locality. The challenge reaches its peak when we consider the universe as a whole. For the entire cosmos, there is no laboratory standing outside it. There is no classical measuring device waiting safely at the edge of space-time to record a result. Any interpretation that relies on a special observer or a firm boundary or an external classical device must explain exactly how its rules apply when every observer, every notebook, and every instrument is locked entirely inside the quantum universe. If you are resting now, letting the abstract concepts wash over you, simply hold on to this core idea. At the scale of the cosmos, the observer and the observed are one and the same. At this ultimate scale, the challenges are severe. Pilot wave theory must find a way to reconcile its guiding equation with relativistic quantum fields and a dynamic, fluctuating space-time. Objective collapse theories need a relativistic mechanism for collapse that does not accidentally break causality. The many worlds interpretation must explain how its branching structure and our familiar three-dimensional reality emerge from inside the abstract mathematics of quantum cosmology. And the relational and informational approaches must clarify whose truth actually matters when the very fabric of space and time becomes uncertain. The practical reason this disagreement has lasted almost a century is simple. The vast majority of working physicists can calculate the results they need without ever having to choose a detailed interpretation, and there is no vote that can decide the truth. A survey of the physics community only reveals what physicists currently prefer, and popularity does not dictate the fundamental structure of reality. We have never proven that one interpretation is the final, unassailable truth. We have also never confirmed that the mystery is inherently unsolvable. And those two statements are not the same thing. The equations agree, the stories do not. And if we cannot yet declare a winner, we can at least appreciate the profound depth of the questions they ask. Next time, we will push these questions to the very edge of physics, where gravity itself joins the fray. We return now one final time to where we began, a quiet night on a university campus in Delft. Two synthetic diamonds resting in separate basements, separated by 1.3 kilometers of optical cable. Two single electron spins entangled in the cold darkness, silently demonstrating a connection that defies our oldest, most trusted classical instincts. 80 years of intense argument culminated in that test, and so it is time to fulfill the promise we made at the start of tonight and cleanly separate what the laboratory has proven from what remains unresolved. First, we know exactly what has been proven. the mathematical machinery of quantum mechanics works flawlessly. It predicts the behavior of the universe with a degree of precision that remains entirely unmatched by any other theory in the history of human thought. It powers our technology and maps the stars, and every interpretation we have discussed tonight accepts that mathematics and uses it without hesitation. Second, we know exactly what has been eliminated. The loophole-free experiments in Delft, Vienna, and Boulder ruled out local hidden variable theories that satisfy the assumptions used to derive Bell's inequalities. No real experiment escapes every conceivable assumption, but the evidence against that family of models is now overwhelming. The universe refuses to be both classical and local, but we must be fiercely precise about this. Eliminating local hidden variables does not mean that every property is completely absent before a measurement, nor does it select a clear winner among the surviving theories. Pilot wave, objective collapse, many worlds, and the quiet informational approaches all survive Bell's theorem intact. Finally, we know what remains completely open. We still do not know if the wavefunction is a physical, vibrating object or a ledger of information. We still do not know why a single, definite outcome is experienced from a vast sea of quantum possibilities. We still do not know the true physical origin of probability. And we do not know what happens to all of those profound questions when space-time itself becomes quantum. The fact that this fierce debate has lasted a century is not a sign that physicists have fundamentally misunderstood the equations. It reveals something much more subtle and strange about the universe. It is entirely possible for a single, wildly successful mathematical structure to support radically different descriptions of what actually exists. The equations agree. The stories do not. And all of those stories now face a severe reckoning. In our next episode, we will follow the physics to the place where every single interpretation struggles. We will step into the realm of quantum gravity. Tonight, every theory we explored was built upon a quiet, unstated assumption that space and time form a smooth, fixed, predictable stage for the particles to perform upon. But general relativity teaches us that the stage itself is dynamic. It bends and it flexes. When we attempt to make the very fabric of space-time into a quantum entity, the old rules break down. We will explore what happens when distance, time, and causality become uncertain, and why the question of what truly exists becomes even harder rather than easier. If you are still awake and listening in the dark, we invite you to follow this podcast wherever you are listening, so you do not miss that journey. And if you have long since drifted off to sleep, letting the electron spins and the abstract wave functions fade away into the night, that is perfectly fine too. The universe will keep turning without us, and the mysteries will still be here waiting for you tomorrow. This is the unknown.